This is a video from section 4.4. The directions say to find the limit. Use L'Hopital's rule where appropriate. Now, if there's a more elementary method of evaluating the limit, consider using it. Now, your goal with L'Hopital's rule is infinity over infinity or 0 over 0. Those are the main forms you have to get the limit in order for L'Hopital's rule to work. Now, let's go ahead and start with this example. So we'll use the next page here. We're going to do example 1. Suppose I had the limit as x goes to infinity of x natural log of 1 minus 1 over x. Now, in its present form, this limit has indeterminate form of infinity times 0. And that's not going to work. And so what I'm going to do is rewrite this limit as follows. So we're going to take the limit as x goes to infinity of, I'm going to leave the natural log of 1 minus 1 over x alone. But in the denominator, I'm going to write 1 over x. Okay? So it's a little trick. And the idea is I use the fact that x is the same as 1 over 1 over x. So I alluded to that in my last video. And if you look, we now have the indeterminate form of 0 over 0, so L'Hopital's rule will apply here. So if I take the limit as x goes to infinity, the derivative of the denominator is negative 1 over x squared. So that's going to come up a lot, right? To take the derivative of the numerator, it's going to be 1 over 1 minus 1 over x times the derivative of 1 minus 1 over x, which is 1 over x squared. I do hope you guys can read that okay. Now, there's still a negative there, but there's a 1 over x squared in the numerator and in the denominator, so I can cancel those. But don't forget that negative. And so this is the limit as x goes to infinity of negative 1 divided by 1 minus 1 over x. But as x gets large, 1 over x is going to go to 0. And so the answer here is negative 1 over 1, which is equal to negative 1. And that would be the correct answer for example 1. Let's take a look at example 2. Now, suppose I had this one. So we'll continue along this same theme. And suppose I had the limit as x goes to infinity of x to the 3 halves sine of 1 over x. Now, this limit in its present form has indeterminate form of type infinity times 0. And we don't want that, okay? So we want to be able to apply L'Hopital's rule, and so what I'm going to do is rewrite the limit this way. So now, I'm going to leave the sign of 1 over x alone. And then I'm going to use the fact that x to the 3 halves is 1 over x to the 3 halves. So I'm going to write that in the denominator like so. Okay? Now, this limit is of indeterminate form of type 0 over 0. And so L'Hopital's rule applies. But before I apply L'Hopital's rule, I'm going to take the limit as x goes to infinity, and I'm just going to rewrite this as sine of 1 over x for the numerator, and the denominator is x to the negative 3 halves. So when I go for L'Hopital's rule, this is the limit as x goes to infinity. The derivative of the numerator is cosine of 1 over x times negative 1 over x squared. So I apply the chain rule. So I'm taking the derivative of 1 over x. The derivative of the denominator is using the power rule. So I'm going to take negative 3 halves x to the, now negative 3 halves minus 1 is negative 5 halves. So I'm going to put negative 5 halves there. So remember, negative 3 halves minus 1 is negative 5 halves. And so also remember that 1 over negative 3 halves is negative 2/3. And so I'm going to move that negative 2/3 out in front of the limit. So I'm going to take the limit as x goes to infinity here. Oh, well, I don't need the fraction anymore, because watch what I'm going to do. I'm going to move that x to negative 5 halves up in front. So I'm going to take x to the 5 halves times 1 over x squared. Make that negative, right? Cosine of 1 over x. Just like this. Now remember, a negative times a negative is a positive. So this is 2/3 the limit as x goes to infinity. And that's, now 5 halves minus 2 is a half. So this is x to the half cosine of 1 over x. But as x gets large, this is going off to infinity. And by the way, that's just a fancy way to say that the limit doesn't exist when you say something like that. That's example 2. Let's take a look at example 3. Suppose I had the limit as x goes to 0 from the right of 1 over x minus 1 over arctangent of x. So this one's a little interesting, because when you approach 0 from the right, I claim you're going to get an indeterminate form of type infinity minus infinity. And this means absolutely nothing. You can't say this is 0. This doesn't make any sense. And so I'm going to manipulate this as follows. Because remember, your goal is infinity over infinity or 0 over 0. Now, if you look at this limit, it looks like I should get a common denominator. And that's exactly what I'm going to do. So I'm going to take the limit as x goes to 0 from the right, and I'm going to get arctangent of x minus x, right? So I just cross multiply and subtract, and I'm going to divide by the product of the denominators, which is x arctangent of x. But if you look at this, and you take that limit, you get the indeterminate form of type 0 over 0, and so this is prime for L'Hopital's rule. So I'm going to take the limit as x goes to 0 from the right of, now the numerator, the derivative of that is 1 over 1 plus x squared, so that's the derivative of arctangent of x, okay? And then I'm going to subtract 1. And I'm going to divide by the derivative of the denominator. But to do that, I got to apply the product rule. So the derivative of x is 1. So I get 1 times arctangent of x plus x times the derivative of arctan x, which is 1 over 1 plus x squared. But when I let x go to 0, I still get indeterminate form of type 0 over 0. Okay? And because of that, I'm going to do L'Hopital's rule again. So it can be a little involved at times. So let's go ahead and rewrite this limit on the next page. So we get the limit as x goes to 0 from the right. Now the numerator is 1 over 1 plus x squared minus 1. The denominator is arctan x plus x over 1 plus x squared. Now, let's go through this again. Now, I'm going to take the derivative of 1 over 1 plus x squared. So that's negative 1 over 1 plus x squared times 2x. So that's chain rule. The derivative of the denominator, okay, is 1 over 1 plus x squared plus, now I'm going to take the bottom function, which is 1 plus x squared, times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 2x, divided by 1 plus x squared, squared. So there's a lot here. Now, so what I'm going to do is I'm going to multiply numerator and denominator by 1 plus x squared squared, because that's what's going to clear the fraction. Okay? And I'll do this, so you know I'm multiplying the whole thing by that. So I'm going to take the limit as x goes to 0 from the right. The numerator is negative 2x. The denominator, I'm going to take this 1 plus x squared squared, I'm going to multiply it by each of those terms. So I'm going to get 1 plus x squared, because there's still one there, plus 1 minus x squared. Because if you look at the numerator up here, it's 1 plus x squared minus 2x squared. So 1 plus x squared minus 2x squared is equal to 1 minus x squared. But the x squareds cancel, and then when I let x go to 0, the answer is 0. So that one is pretty intense. And that was example 3. So let's take a look at example 4. I'm going to go over this one. We need to be exposed to this. Suppose I had the limit as x goes to infinity of x to the 1 over x. Now this limit has indeterminate form of type infinity to the 0. And we don't want that, okay? So this is how you approach a problem like this. So we're going to set y equal to x to the 1 over x. Now, so what we're going to do is take the natural log of both sides. So natural log of y is natural log of x to the 1 over x. Okay? Now, I'm going to move the 1 over x to the outside of the log. So natural log of y is 1 over x ln of x. And so what I'm going to do is, instead of taking the limit of x to the 1 over x as x goes to infinity, I'm going to look at this limit here. So the limit as x goes to infinity of, we'll say, natural log of y is the limit as x goes to infinity of natural log of x over x. And where did I get that? Remember that 1 over x times natural log of x. I'm just rewriting that as ln of x over x. Okay? And so now I'm in a position to apply L'Hopital's rule, because this has indeterminate form of type infinity over infinity. So I'm looking at the limit as x goes to infinity. The derivative of the numerator is 1 over x. The derivative of the denominator is 1. But as x gets large, this goes to 0. So what we know is that the limit as x goes to infinity of ln of y is 0. Also, what you want to know is e to the natural log of y is the same as y. That allows us to take the limit as x goes to infinity of y, which is equal to e to the 0, which is equal to 1. But y is x to the 1 over x. And we're done. Therefore, the limit as x goes to infinity of x to the 1 over x is 1. So I'm going to do one more problem in that theme for this video. So example 5, we get the limit as x goes to infinity of e to the x plus 10x to the 1 over x. Now, this limit has indeterminate form of type infinity to the 0. So I don't want that. And I want to put myself in a position to use L'Hopital's rule. So I'm going to set y equal to e to the x plus 10x to the 1 over x, like so. I'm going to take the natural log of both sides. But I'm going to move that 1 over x out in front of the log. So natural log of y is 1 over x ln of e to the x plus 10x. Okay? And so I'm going to take a look at the limit as x goes to infinity of ln of y. But that's the limit as x goes to infinity. And if you don't mind, I'm going to write this as natural log of e to the x plus 10x divided by x. Now, this limit that I'm putting a sort of kind of rectangle, looks more like a parallelogram, around, this limit has the form infinity over infinity. Then that's perfect, because now I can apply L'Hopital's rule. I can't apply L'Hopital's rule on infinity to the 0. That doesn't make any sense. Okay? And so this is the limit as x goes to infinity of. Now, the derivative of x is 1. The derivative of the numerator is 1 over e to the x plus 10x times the derivative of the stuff inside, which is e to the x plus 10. Okay? And then this is the limit as x gets big of e to the x plus 10 divided by e to the x plus 10x. Now, we still have indeterminate form of type infinity over infinity, So L'Hopital's rule still applies. So this is the limit as x goes to infinity of the derivative of the numerator is e to the x. The derivative of the denominator is e to the x plus 10. Now, you could do L'Hopital's rule again. Here I would say you don't have to. What I'm going to do is divide the numerator and denominator by e to the x. So I have e to the x over e to the x divided by e to the x over e to the x plus 10 over e to the x. So this is the limit as x goes to infinity of 1 over 1 plus 10 over e to the x. But that's 1. Okay, after all that work. So what that says is the limit as x goes to infinity of natural log of y is 1. But y is e to the natural log of y. Okay? And so therefore, the limit as x goes to infinity of y is e to the first. But y, so let's go back. If we go back to the previous page, y is equal to e to the x plus 10x to the 1 over x. So it looks like that limit is actually e. And that's going to conclude this video for section 4.4, where we did 5 more examples. Okay, thank you.